Thanks very much. I hope you appreciate the effort that the organizers have gone into preserving a thematic continuity. First, we heard from a brilliant and passionate inventor who wants to help amputees, and then who comes on next? I'm going to be talking to you today about research which I do in my labs mostly, and mostly with older students, juniors, seniors, graduate students, and so on. But I did want to mention that, in fact, I also am, of course, a classroom teacher at the University of Colorado, and I tend to specialize in the younger students, the freshmen and the sophomore, who are more fun, really. And I did the math the other day. Over the last 10 years, I think I've had in my class about 1,500 freshmen and sophomores over the last decade or so, including, I'm very proud to say, yes, Alan Sanchez, who we heard from just a few minutes ago. Okay, so what happens in the research in my laboratory work? What do they make in Eric's lab? What do we make in Eric's lab? The answer is we make the world's coldest stuff. What do I mean by the world's coldest stuff? I want to get an idea of give you an idea of just exactly how cold I mean. And to do that, I have to drown you in a little jargon here. Physicists, we measure things in Kelvin, starting with the lowest possible temperature, absolute zero, calling that zero, and going all the way up to room temperature, say 295 degrees Kelvin, which is about room temperature 71. And we think of freezing, 32 Fahrenheit, as being a lot less than room temperature. But from our point of view in the lab, 295, 273, it's about the same. The lowest temperature they ever measured in Colorado was in Moffett in 1985, and they got down to minus 61 Fahrenheit. And still, as far as we're concerned, that's still in the 200s. The lowest temperature they ever measured on the surface of the Earth was in Antarctica. And yeah, okay, now at least at minus 128 Fahrenheit, we're getting down into the 100s of Kelvin, but we have a ways to go. Heading down to the temperatures where we work at, 77 Kelvin, that's where air turns into a liquid. 4 Kelvin, that's where helium turns into a liquid. The lowest possible natural temperature you could ever encounter is in the interstellar space, far away from any other stars. And even there, it doesn't get all the way down to absolute zero. It gets down to about 3 Kelvin. Where I'm going with this is that, for us, this is still almost impossibly hot. 3 Kelvin doesn't even count. 1 Kelvin is about how low you can get with the traditional refrigerators. 2 millikelvin, 2/1000ths of a degree above absolute zero, is the lowest temperature you can get with the old school cryogenic refrigerators, and still, by our standards, way too hot. From there, we head down. There's a technique called laser cooling. Seems a little counterintuitive, but you can get to extraordinarily low temperatures using lasers, and we get to within about 2 millionths of a degree, 2 microkelvin of absolute zero, still way too hot. In the mid-90s, we got down to 200 nanokelvin, and just a few months after that, finally, we got all the way down to what was then the world's lowest temperature by a long ways, 20 nanokelvin, 20 billionths of a degree above absolute zero, which is where Bose-Einstein condensation happened. Unfortunately, I don't get an hour to tell you all about Bose-Einstein condensation, but I will show you a picture of it. On the left, you can see sort of a swirly, multicolored gas, which is at about 400 nanokelvin. And in this particular run, the Bose-Einstein condensation appears around 50 nanokelvin. It's that shark's fin shape there. And we've spent some 20 years since then describing it, learning about it, finding out what it's good for. But I really sort of mostly want to talk to you about is the people who did it, and by that I don't really mean me, I mean people like this. This is the group of students and their partners reassembled a few years later in Stockholm for the Nobel Prize. Don't they look cute? in their monkey suits and what have you, yeah. And this actually gets back to what I really I think of as maybe more important when we say, what is it that we make in my lab? The world's coldest stuff, true, yes, but also what we make is highly trained, cutting-edge, young technology people. And here are some of them. Getting to these extraordinarily low temperatures then and now, and especially now that we've gone to lower temperatures and on in new directions, requires doing technological things that weren't possible, weren't really even imaginable in the 1990s. The kind of skills that you learn to do that are skills, they're not any particular cutting edge skill, they're really cutting edge attitudes. I tell my students that after 4 or 5 years working in my lab, I want them to be all around technological badasses. No excuses, if there's a problem, you solve it. There's some more of these students over the years, going back a little further in time. I show my colleague Debbie Jin, who also got her training at the University of Colorado, not a fully young person in this picture, but was, at the time of her untimely death a couple of years ago, probably one of the 2 or 3 best female physicists in the world. Here's Tanya, now following in her footsteps. In the back, far away on the back there, you can see a blonde woman who's Professor Heather Lewandowski. She was actually a University of Colorado graduate student, now a technological leader in her own right at the University of Colorado in the physics department. She stopped by, I ran into her in the hallway the other day, and she said, "Oh, I've got this great technological idea. It's for a really cool experiment. Unfortunately, we need a high voltage amplifier whose specs far exceed anything that we can buy." And I said, "Well, is that a problem?" She says, "Well, it means we're going to have to invent a new high voltage amplifier." And I said, "Oh, so what you're saying is not a problem?" She said, "Not a problem." And she and her graduate students did invent one, for which they now have a patent pending. I guess the idea is that skills can expire, but attitudes can't. You go into this with sort of a free-swinging attitude of technological confidence, and it's really what makes all the difference. Show a few more pictures here, students over the years. How do we get things so very cold? 2 different ways. We use magnets and we use lasers. And I realize that seems a little hokey. The magnets don't look like those magnets, and the lasers don't look like those lasers. But unfortunately, I don't have time to tell you about it. Why do we get things so cold? One reason we need to get things so cold is, I call it super freon. There's this idea called quantum computing, which is sort of a new idea for computing. It's really the hottest idea in computing these days, to make computers like this. And so far, it's not actually commercially viable or even technologically viable. It's just an idea that a lot of people are excited about. What all quantum computing ideas have in common is they need to be very, very cold. Freon, no one has anymore, but it used to be the stuff that was in your air conditioner. One way or another, you need to get your quantum computers cold if they have a hope of working. A lot of times they're actually sitting in a bath of liquid helium. Still colder yet would be sitting in a bath of Bose-Einstein condensation. And some of the most promising ideas for quantum computers involve actually sort of being immersed in a Bose-Einstein condensate. That's one reason. That's one reason why we want to do it. Another reason is that it's hard. It's exactly the kind of problem that you can cut your teeth on, that you can work your technological muscles against, where you have a challenge which is worthy of the name. So the students that come out of this process, out of the CU physics program, out of the CU sciences program, some of them go off to universities. A lot of them start their own companies. This is Vesson Photomics. Founder and CEO is a CU physics student, and about half of those employees came out of CU physics. There's let's see, that's Precision Photonics, another company. Excuse me. And Captain Murnane Laboratory, another company which was founded not by students at CU, but by 2 CU professors, Margaret Murnon and Henry Captain. But at least half the people who work there are out of our physics program. Recently, a lot of people were hired by Honeywell. Honeywell moved to Broomfield, Colorado, built a new facility there, and every time I ran into one of my old students somewhere in the Pearl Street Mall, they would tell me, yeah, we're working for Honeywell now. Can't tell you what we're working on, but it's really cool. Some sort of proprietary thing. I actually, because they wouldn't tell me, I finally went to the Honeywell website and typed in Broomfield under the employment thing, and what came up was just dozens and dozens of jobs. And if you look at those titles, those are basically various different ways of saying CU students. So in all sorts of different categories, all sorts of different focuses, different specialties. And you know why they want to hire them, because they are all around technological badasses. Thank you very much.